Introduction to Collinear Vectors. Hello everyone. Today we are going to begin a new topic in our study of vector algebra, collinear vectors. To start off, let's look at what the term collinear actually means in a geometric sense. When we talk about collinearity, we are essentially discussing the geometric alignment of vectors. Now, up until this point in our course, you have often been used to thinking of vectors as specific arrows that start from a fixed, particular point. However, as we move into the concept of collinearity, I want you to shift your focus. Instead of worrying about where a vector begins, we are going to focus on its line of action. This refers to the infinite straight line that the vector lies upon, or the line that the vector is parallel to. Keep this idea of the line of action in mind, because in the next slide, we will break down exactly how this allows vectors to be collinear, even if they aren't on the exact same path. Understanding collinear vectors. Now that we have introduced the basic idea that collinearity is all about geometric alignment, let's dive deeper. To really grasp what makes vectors collinear, we are going to break the concept down into three manageable components: the line of action, direction, and magnitude. First, let's look at the line of action. Think back to our introduction, where I mentioned that we focus on the path the vector follows. A vector is considered collinear if it is parallel to a specific given line. If we have two, or even more, vectors that are all parallel to that same line, we call them collinear vectors. It is very important to note that these vectors do not actually have to sit on the exact same physical line. They just need to share that same parallel orientation. Second, let's discuss the independence of direction. This is a point where many students get tripped up. Collinear vectors do not need to point in the same direction. You can have two vectors that are collinear because they point in the exact same direction, but they are also considered collinear if they point in exactly opposite directions. As long as they follow that same parallel path, the direction doesn't break the collinearity. Finally, we have the independence of magnitude. This means that the length or the magnitude of the vectors does not affect whether they are collinear. It doesn't matter if one vector is twice as long as another, or if one is significantly shorter. As long as they remain parallel to that same line of action, they remain collinear. In the next slide, I will show you how we express this relationship using a formal mathematical formula. Mathematical representation. Mathematically speaking, if we have two non-zero vectors, let's call them vector A and vector B, they are considered collinear if one can be expressed as a scalar multiple of the other. In notation, we write this as vector A equals lambda, the Greek letter lambda, multiplied by vector B. In this equation, lambda represents a non-zero scalar, which is just a fancy way of saying a regular number. This single number, lambda, is the key to understanding the relationship between the two vectors. If lambda is greater than 0, it means the scaling factor is positive, so the vectors are collinear and point in the exact same direction. However, if lambda is less than 0, the negative sign flips the direction, meaning the vectors are still collinear because they lie on the same line of action, but they are now pointing in exactly opposite directions. Now that we have a conceptual grasp of what collinearity means in terms of direction and line of action, let's move from the visual idea to the formal mathematical language. This is where we can actually prove whether two vectors are collinear using algebra. Keep this formula in mind, because it is the most important tool you will use when solving problems involving collinearity. Real-world example: traffic on a straight highway. Now that we have covered the mathematical definition and the concept of scalar multiples, let's bring this all together with a practical, real-world example. I want you to imagine a perfectly straight stretch of a highway. On this highway, we have two vehicles, car A and car B, both in motion. Let's break this down step by step to see how the principles of collinearity apply here. First, let's look at the line of action we discussed in the previous slide. In this scenario, the straight highway itself acts as our common line of action. As long as the cars are traveling along this specific path, they are aligned with this line. Now, let's consider our first scenario. Suppose both car A and car B are driving north. If we represent their velocities as vector v sub 1 and vector v sub 2, you'll notice that both vectors are parallel to the highway and are pointing in the exact same direction. Because they share this alignment, they are collinear. But what if they aren't going the same way? Let's look at scenario 2. Imagine car A is driving north, but car B is driving south. Even though their velocity vectors, v sub 1 and v sub 2, are pointing in opposite directions, they are still traveling along that same straight highway. As we learned earlier, direction doesn't have to be identical for collinearity to exist, so they remain collinear. Finally, let's look at scenario 3, which addresses the idea of magnitude. Suppose car A is cruising at 60 kilometers per hour, while car B is moving much faster, at 100 kilometers per hour. Even though the lengths of our vectors, their magnitudes, are different, the fact remains that they both follow the path of the same straight highway. Therefore, they are still collinear. This example perfectly illustrates that as long as the line of action is the same, the direction and the speed do not change the collinear nature of the vectors. Now, before we move on, let's pause and look at some common pitfalls where students often get tripped up. Common mistakes to avoid. First, please be careful not to confuse collinear with equal. It is a very common mistake to assume that if two vectors are collinear, they must be identical. However, remember what we discussed regarding magnitude earlier. For vectors to be equal, they must have the exact same magnitude and the exact same direction. Collinear vectors are much more flexible. They only need to share that same line of action or be parallel to it. Second, don't fall into the trap of assuming that collinear vectors must point in the same direction. As we saw in our highway example with the cars driving north and south, vectors can be anti-parallel, meaning they point in exactly opposite directions and still be perfectly collinear. As long as they follow the same line, the direction doesn't break the collinearity. Finally, let's talk about positioning. You might be tempted to think that these vectors must all start from the same origin point. But remember, in our study of vector algebra, we are dealing with free vectors. This means these vectors can be located anywhere in space. They don't need to be touching or starting from the same spot. They simply need to maintain a direction that is parallel to that same common line. Now, before we wrap up and summarize our key takeaways, I want to pause and address some common pitfalls. I've noticed that even bright students often stumble on a few specific points when dealing with collinearity, so let's clear those up right now. Keep these distinctions in mind, and you'll avoid the most frequent errors in your calculations. Now, let's move to our final slide to consolidate everything we've learned today. Key takeaways. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session on collinear vectors to ensure everything is clear before we move on to our practice problems. First, let's revisit the core definition. Vectors are considered collinear if they are parallel to the same line. As we discussed earlier with the line of action concept, they don't even need to be on the same physical path. They just need to share that same parallel orientation. Second, regarding direction, remember that direction is flexible here. Collinear vectors can point in the exact same direction, or they can point in exactly opposite directions. Both scenarios satisfy the condition of collinearity. Third, let's not forget the magnitude. The length or size of the vectors does not influence whether they are collinear. Whether one vector is much longer or much shorter than the other, as long as they remain parallel to that same line, they stay collinear. Finally, if you are looking for the mathematical test to use in your calculations, remember this condition. Vector A and vector B are collinear if vector A equals lambda times vector B, where lambda is some scalar. This scalar relationship is the mathematical proof that one vector is simply a scaled version of the other. Keep these points in mind, as they are the foundation for the more complex vector operations we will tackle in our next lesson.